Natalia Berloff from this nice university town, talking about modeling and non-equilibrium condensates.
Okay, thank you. I also would like to thank organizers for the opportunity to speak. And what I'm going to talk about are different models. Actually, I will introduce two models of a newly discovered condensate that are actually non-equilibrium condensates that exist in solid-state physics nowadays. These systems are not going to be in thermodynamical equilibrium, so they will have some gain and loss terms, and that brings up some quite interesting dynamics. So I will contrast it and compare with the standard dynamics in equilibrium systems. So acknowledgement, this work was done with my postdoc, Magnus Bohr, who is now moved to Southampton just 1 month ago, and a colleague, Jonathan Keeling, who just started his faculty position at St. Andrews University. And it's based on these two publications plus some newer results. Okay, so first I will speak shortly about what these condensates are, solid-state quantum condensates, with emphasis on exciton-polariton condensates, half light, half matter condensates. I will introduce Gross-Pitaevsky equation with loss and gain, which is really the complex Ginzburg, a particular limit of complex Ginzburg-Landau equation, and we'll discuss some states, like stationary state. I will discuss vortices and then vortex lattices. Then, by taking into account spin degree of freedom in these condensates, I will introduce another system, and then I would be interested in interplay between interconversion and detuning created by magnetic field. And in particularly, for these systems, I would be interested in stability of cross-polarized vortices, so when you have two vortices of opposite circulation sitting on top of each other, and I will discuss synchronization, desynchronization in these systems. Okay, so what these exciton-polariton condensates are, the idea is that absorption of a photon by semiconductor microcavity excites exciton, electron-hole pair. Exciton is an excited state, so it's highly unstable, so it tends to emit photon back. If the mirrors are placed in resonance with exciton, then the photon will be reflected back in, will be reabsorbed, re-emitted, reabsorbed, re-emitted, etc. So classically you have exciton, photon, but in quantum superposition of states, that creates another quasi-particle called polariton. And polaritons, since they're made of light and matter, are very light. Actually, they just 10 to the minus 4 and 10 to the minus 5 in some circumstances of the mass of the electron. And as we all well know, the temperature for the transition to condensate state, to the Bose-Einstein condensation, is inversely proportional to the mass of the particle, which implies that for this condensate, the transition temperature is rather high in comparison with other superfluid or condensate systems. For superfluid helium-4, we are talking about few Kelvin, 2 Kelvin. For helium-3, that's microkelvin. For ultra-cold gases, BC, we're talking about nanokelvin temperatures. So here we're talking about 20 Kelvin for some system, cadmium telluride, for instance, and there are now new systems for which this condensation has been achieved at actually room temperature, which opens a new road to really creation some spintronic atomic precision measurement devices. So there is a lot of interest in these systems. So I would like to say maybe more carefully about this process of the photon-exciton superposition, so how the actual system works. So semiconductor microcavity is a Fabry-Perot resonator with two Bragg mirrors in resonance with a planar, with the exciton on a quantum well, which is a planar system. So it's really a 2D system. That's where excitons live. The laser are two types of the experiment. So now you have this superposition of the photon and exciton. So these Bragg mirrors are placed half an integer of the wavelength of the light, so that they are in a resonance with the exciton. So there are these particles, therefore, made of the superposition of the eigenmodes created by photon and exciton, creating lower polariton branch and upper polariton branch. And this is where the condensation will take place. There are two types of experiments in which, in the first, there is a coherent light shining, so creating polaritons at particular momentum position, and then they scatter into the signal state and idler state. But I would be more interested in incoherent condensation, in which the laser beam that creates the photons is really shined at energies much higher than the slower polariton branch, so it creates an incoherent source of polaritons. These polaritons scatter, reconnect, recombine, emit phonons, so they recombine optically and acoustically, and finally get into the bottom of this lower polariton branch. Meanwhile, there are photons that are escaped, so that these Bragg mirrors are imperfect, so some of the photons actually escape, so this system has to be continuously repopulated to keep the steady state, to keep the condensate actually in this position. So this is the difference with the standard equilibrium systems, in which you don't have the large losses in the system. Here it has to be continuous, so the laser beam has to continuously shine, provide this source of free carriers, polaritons, and only that will then maintain the condensate in a lower polariton branch. Okay, so the first experiments were done in Lausanne and Grenoble in 2006. And they actually, by measuring this, so the beauty of the system is that the photons, when they escape, they actually carry all information, the continuation of the wave function of the condensate, so they carry all information about the condensate in the semiconductor microcavity. So we can resolve it actually spatially and in the momentum space to see this narrowing. After these first experiments, a lot of questions remained. For instance, this coherent emission, this coherence created by the condensate, has been seen only in the region excited by laser. So it wasn't clear to which extent the coherence we see is actually coherence due to condensate rather than coherence due to laser itself. Secondly, cadmium telluride, the material which has been used in these experiments, is very irregular. So there are a lot of local minima, local maxima. So it's very disordered. Ground state was not poorly defined. It wasn't clear whether you have individual condensate in this local minima or there is a coherence across the entire sample. So to some extent, it's been remedied. Some of these questions has been answered in the set of experiments done by David Snoke and Pittsburgh, where they used gallium arsenide, a much more regular material, and then they applied, to create the trap, they applied a very smart technique of actually squeezing the sample with two pins. Physically squeezing material shifts the energy levels, creating effectively a harmonic trap. The same trap used in equilibrium ultra-cold Bose gases. And then you could shine your laser away from the minimum of the trap and to see condensation in the middle of the trap. So you can therefore separate the coherence due to laser and coherence due to the condensate. And they've seen this very clear signature of BEC, spatial and spectral narrowing. They could measure the coherence. So it was a much clean experiment in many respects. So what is shown here is the cloud before the criticality, at the criticality, and then these correspond to the condensed states. These are the density states, not the momentum states, what you see here. And you see immediately that there is a quite striking difference with the condensate in ultra-cold gases, where the gas is actually resembles the inverted parabola. That's the density profile. And even more so, the more strongly interacting gases will give you even wider spread for this inverted parabola. Exciton polariton condensates are stronger interacting gases than ultra-cold BECs, but in spite of that, you see that the density of the cloud is quite different. You have a narrow peak in the middle, and then the widening after that. So peak in the middle, then widening away from the center of the trap. So the first question that we were interested in really was how to explain, how to get these stationary steady states in the exciton polariton condensate that give us this distribution of the particles. But before I go to the model, immediately I wanted to mention this, that immediately after the discovery of these exciton polariton condensate that are not in thermodynamical equilibrium, there was the debate started to which extent these are really superfluid systems. And so we also contributed to this discussion somewhat. And our idea was that superfluidity is a complex phenomena, and there are several aspects of that. So for instance, you have a superfluid system has to have quantized vortices. They have to be Landau critical velocity below which excitations cannot be created. Metastable persistent flow in a toroidal geometry has to exist. It has to be the description available in terms of two fluid hydrodynamics representing superfluid component and normal fluid, the thermal cloud. They have to be local thermodynamical equilibrium. They have to be some solitary waves present in the system. And only this standard superfluid system like helium-4, helium-3 and called atom BECs actually tick all the boxes. There are other systems that are not superfluid, for instance, non-interacting BEC gas, for which there are some ticks and some crosses, some things that cannot be created in these systems. Even the classical rotational fluid actually has some ticks. So this incoherently pumped polariton condensate that I will talk about, they have already some crosses. We know that it's not thermodynamical equilibrium. We know that the modes are diffusive rather than linear for small momenta, so there is no Landau critical velocity. But what I'm going to talk about are quantized vortices. There are now some results appearing on metastable persistent flow, and in my talk I will also touch upon possibility of creating solitary waves, so all the signatures of the actual superfluid system. So for the model for exciton polariton condensate, we use the basis of Gross-Pitaevsky equation with external trap, which is again a parabolic harmonic oscillator trap. Now we have linear gain and non-linear losses. So there are several reasons for us to introduce in this effective net gain to be linear and losses being non-linear. So first of all, it's clear that losses and gain should have different order in non-linearity, otherwise they will just, whichever is bigger wins, in other sense. You either have only gain, either have losses. So you have a difference in non-linearity in order for them to saturate each other. This model can be obtained.
I have a question. You just said, maybe I just didn't hear correctly. You said that here we deal with strongly interacting systems. So then how can one write a mean fluid theory?
So in the terms of how strongly this system interacts, it lies somewhat between helium and weakly interacting both gases. So it's not as weakly interacting as the gases, but it's much weakly interacting than superfluid helium. And you're right, there is no rigorous definition in terms of for ultra-cold gases. From Heisenberg representation, we can derive Gross-Pitaevsky rigorously from first principles. Here, this derivation cannot be made precisely for the point you cannot separate highly occupied modes from lowly occupied modes. Nevertheless, to some phenomenological extent, that's possible. And the idea is that you can write down the Hamiltonian for the system.
But also for helium, people write that.
Yeah, even for helium, there are attempts, and you can. So for the long wavelength, so there are regimes, and there is this idea that once you write down this general equation that gives the macroscopic occupation, that describes the macroscopic occupation of the sum modes, yes, for these systems, it's not rigorous, but phenomenologically, that can be a reasonable idea. And as you can see, actually, this model already scored a number of successes in predicting and explaining some of the experiments. But it cannot be derived as rigorous as for weakly interacting gases, yes. What can be done, how these terms can be obtained, and this is where, maybe I should say a few more words about it. For instance, what can be done in the system to derive these terms, or to derive the whole model directly? You can write down the Hamiltonian describing the condensate system interacting with the reservoir of free carriers and deriving the reservoir of the escaping photons. And then this is non-equilibrium system, so the interactions between these different reservoirs can be used, you can use the Keldysh non-equilibrium path integration formalism. And then in this formalism, you can get the steady state or saddle point representation. And then from this steady point representation, you can take Taylor expansion. But this stage, that's exactly, you can only do Taylor expansion if you assume that there is a small parameter that the interactions are weak. So this is where the problem comes. If you formally do that, then indeed from this formalism you recover these two terms. But this step is not rigorously justified. That's where the problem is. Okay. So from the experiment, by dimensionalizing from the experiments, if we dimensionalize this model, we actually left with just two parameters that represent the gain and the loss, alpha and sigma. And then from the experiments, we can estimate and see that these parameters have the range, alpha gain is between 0 and 10 in our non-dimensional units, and losses are about 0.3. That's how well we can estimate this. Okay, so what about this radially symmetric stationary states? So looking for the stationary states, we introduce the chemical potential, and first we can assume that the gain is not large. The losses are not large, we know that. So, but if alpha is not large, then the Thomas Fermi solution, the same as for ultra-cold gases, for equilibrium system, this inverted parabola can be written down. So we neglected this term, so that's just a trivial consequence of that. Then by the integrating this, by taking this and the complex conjugate and integrating, we actually plotting this solution, we can get the estimate for the chemical potential is just 3/2 of alpha over sigma. And then as usual, we write the Modellang transformation for density in the phase. And now we can see, so this comes from the conservation of mass, so actually for the mass continuity. So we can see that if density is low, then gain dominates. So where mass is low, that's when the system provides the gain. When mass is high, then the dissipative term dominates. That's where the mass is being taken away. So we know that now we have regions of high density where the mass is being lost, low density region when mass is being gained. Therefore, we have to have fluxes that connect these regions. So there are currents. And actually in Thomas Fermi regime, we can estimate analytically what these currents are. So it's zero velocity outside. It has to be zero in the center because of the symmetry. And then the velocity, so the currents take their maximum value somewhere in amplitude, somewhere in between. And then to preserve the chemical potential, therefore, that's where the density has to drop, if I just neglect this term for the moment. So large currents lead density depletion. And so now if we go back to this system, we can solve it also numerically and to see that indeed if these parameters are small, then my solution, the red curve, agrees with the Thomas Fermi profile shown in black. But as the gain grows, so this is now medium gain, we have this narrow peak in the middle and then the widening outside, again contrasted with this Thomas Fermi profile. And as alpha goes even higher, we have again even more narrow peak in the middle and then the widening on the outside, and this point actually coincides to where the fluxes are maximum. So we saw that we were happy that our system seemed to explain that, so then we could look at the vortices, again use the ansatz for the vortices of the circulation S, and now we take into account also the radial fluxes that exist, substitute in the Gross-Pitayevsky and get first of all numerical solution for the amplitude and the velocity of the vortex. And also we can see that for the velocity from the asymptotics, we can see that the velocity is actually positive for small r, so there is an outflow of the mass from the center of the vortex. So in this diagram, so this is the velocity, this is for the vortex-free solution, this is small r, so small distance away from the center of the trap, and this corresponds to the winding number, to this number S here. And so you see this, the bigger is the winding number, the wider is the region that the velocity is positive. There is an outflow of the mass from the center of the vortex. So actually it implies that you have a radial fluxes towards the center, and then the flux is away from the center coming from the vortex. So these are really spiral vortices. If I look at the phase, that the phase goes around, but then it changes the sign as it comes to the center of the vortex. And soon after we discuss these vortices, indeed the spiral vortices have been observed in Grenoble experiments. And again, you can see even that, so this is the phase, you can see that the spiral indeed changes its phase as it comes to the center of the vortex. So to some extent, I mean, the resolution is not terribly good, but it suggests that it indeed changes its direction. Okay, so we were happy for about a day when we saw that indeed we can predict this the right structure, and we can see vortices, and we can see explain the peak of the density. And the reason why our happiness didn't last long, because we realized that these solutions are unstable. And it's easy to see why they are unstable, because remember, we pump everywhere. It's a constant pump. This is our Thomas Fermi profile, this inverted parabola. This is the trap, and these are the states that we found with the peak in the center. If I look at my hydrodynamical equation and neglect the quantum pressure term, I can see that for these regions where the density is small, this term can be neglected, so my system sees only gain that cannot be compensated by any losses. So this is the source of the instability here, only gain. And we can formalize this to see which mode becomes unstable first by extending analysis done by Stringari for ultra-cold gases when he established what are the modes, stable modes in equilibrium condensates. And we can extend it by again treating gain and losses as a small parameters that appear in a first order correction. And then for the normal modes of 2D, in 2D trap, we have the usual Stringari ansatz, and then when we add this weak pumping and decay, then we can see that there are these modes, so that for every n here, we can find m, the angular mode, sufficiently high, so that this becomes negative, leading to, therefore, exponential growth of those modes. So for each system, sufficiently high angular modes get excited and lead to the instability. So what is the, how can we get out of this? Actually, but in experiments, it's always a finite spot of the laser that's being used, and actually the radius of the spot is comparable to the Thomas Fermi radius. It's very hard to make the laser to have a laser spot bigger than that, because then it leads to thermalization of your cloud, increases effectively the temperature. So then we have to model it by, instead of using the uniform gain everywhere, we have now gain inside the circle of radius R0. So if we'll do that, so now we only pump on the finite radius, that actually stabilizes the radially symmetric modes and vortex modes, so we're back into play. Very happy. Explain the densities, now predicted the vortices, but now the question is, what if I make my laser still be of the finite size, but the size slightly higher than the Thomas Fermi radius, so I still have this high frequency modes excited. So what is the outcome of this instability? So how to check it? Okay, just get the larger radius of the spot, put it in the computer, and that was the result of the evolution in time. So we start with the Thomas Fermi. So what you see are the density plots. The red shows the radius of the pumping spot. So it's slightly above the Thomas Fermi. So initially, actually, system brings about this state with a peak in the middle. And it stays there for quite significant time. Then you can see that these angular modes become excited. And then the vortices enter the system into pairs, positive and negative. It's quite irregular, chaotic behavior after that. After that, the vortices of only one sign finally win. They form a regular lattice that starts to rotate uniformly. And in this case, so you have a lattice of 5 vortices. That's not the final state. So system again excites another round of high frequency modes, another vortices come in, but after a while the system settles to this 6 vortices in the solid body rotation. So that came as quite a shock, because remember, the vortex lattices have been seen in equilibrium BEC gases, but there is always a rotation involved. So that comes, the angular momentum in those systems is provided by the rotation. Of course, we heard of Abrikosov lattices, but in that case, the magnetic field, again, plays the role of the rotation. So any system that we've seen before, superfluid helium, the rotating bucket creates a lattice of vortices. So in all this system, there is a rotation external to the system. Here there is no external rotation. So this lattice forms from the symmetry breaking mechanism. And the lattice rotates in positive or negative sense simply depending on what kind of noise is present in the system. So how can we understand where these solutions are coming from? So first I can increase, so this picture for instance illustrates, I increase the radius of the pumping spot even further, and so now I have around 70 vortices in the system. So the larger the radius is, the more and more vortices coming into the system. There is some hysteresis in the number of actual vortices formed depending on the initial state. If I plot the density of the lattice, so this is the average density across the slice, so averaged over the angle. So you can see that it became flattened. Again, in ultra-cold gases, the vortices are superimposed on an inverted parabola. Here it became completely flat. So now I can summarize the findings. So I can plot the chemical potential of the solution versus the radius of the pumping spot versus this. So if the Thomas Fermi radius is somewhere here, so that's my critical radius. So below this radius, we can have stable solutions. These are radially symmetric vortex-free solutions. And then the numbers indicate other solutions that have vortices. So these numbers correspond to the number of vortices. So I can also have my spiral vortex, but to have this vortex, I have to put it by hand. For instance, by using a laser beam again to create the circulation. I can have 2 spiral vortices, 3 spiral vortices, but above the criticality, the radially symmetric profile as well as these states become unstable, and then there is this spontaneous formation of the vortex lattice, bringing up various number of vortices. So how do I know that this is a solution and not artifact of the computations? So if I reformulate my problem in a rotating frame, and again, time depends, so in a rotating frame, assuming that the lattice is in a solid body rotation, uniform rotation, that is a steady state. And then I can see that I indeed have a self-sufficient, self-consistent solution to the system. If again I drop the chemical potential term, I assume that I'm away from the boundaries, and then the solid state rotation implies that the gradient of the phase is exactly that. So these 2 terms go away. From this, then I conclude that the density is gain over losses. So that gives me my flat density distribution here. That goes away. Density, therefore, the chemical potential is alpha over sigma, the same that I saw numerically. And then I can see that the angular velocity of the rotation is just 1, plus or minus 1. If I go back to my dimensional units, it means this omega corresponds to the frequency, the natural frequency of the trap. So the role of the vortex lattice is, first of all, to fill in the pumping spot by bringing in the vortices. Second role is to cancel the natural frequency of the trap. That allows to create this uniform density profile. Okay. Without any external rotation present. So that can be used for signal processing, because it can be used for very accurate gyroscopes, because it gives it amplifies the rotation in one particular sense, depending on some small noise present in the system. Okay. So my results so far didn't involve polariton spin, although there were experiments again in Grenoble that showed that by separating left and right circular polarized polariton states, that for instance it's possible to have a vortex in one polarization but not another, and actually they observed all possible combination of vortex states. Perhaps I should say a few words about how the spin becomes important in this system. So polariton, exciton polariton quasi-particle consists of the photon and exciton. Now photon, being light, it has spin plus or minus. exciton can have spin plus or minus 1, plus or minus 2. But the plus or minus 2 dark states are not allowed by rules of optical absorption. And actually they will have the energy much higher than the energy of the condensate state. So now you have only plus or minus spin combined for the exciton polariton. Okay? So polariton behaves like an electron. It's a two-level system, so it can be described, uniquely characterized by pseudospin. So if the pseudospin is in a direction, so I'm talking about the projection on the axis of the growth of the structure. So if the pseudospin aligned with the axis of the growth of the structure, so orthogonal to the plane where exciton live, then you have circularly polarized light. So it's either left or right polarization survives. But if the pseudospin is in the plane of the exciton, then the polarization will be linear, so that both polarization come in equal proportions. And if the pseudospin is anywhere in between, you have an elliptical polarization, where density of one state of one polarization is higher than the other. So how to take into account the spin degree of freedom? So let me recall that for weakly interacting Bose-gas model, we have these terms: kinetic energy for the one component, kinetic energy for the other component, and then the coupling between these two. There is a tendency to bi-exciton formation, so that brings about this interaction term. And actually in exciton-polariton condensate, the interaction between each polarization are strongly repulsive, and the interaction between different polarization are weakly attractive. Okay, so that's the sign of that. We can apply a magnetic field that favors one polarization over the other. And by driving a magnetic field, the system, therefore, can go through the phase transition. Again, if there is no magnetic field, then you have equal proportion of left and right circularly polarized polariton polarizations. As the magnetic field increases, then the density of one component, in this case it favors the left component, increases, the density of the right component decreases. If it becomes too high, then you're left with just one component, so it's a circularly polarized condensate. There are other terms that I have to add to my Hamiltonian, because the crystal, the underlying for this quantum well crystal, is non-centric. So there are some two axes preferred direction for the underlying crystal. So you have circular symmetry is broken, you have two equivalent axes bringing up this term. Other non-symmetries, for instance, the interfaces between quantum wells actually break even this symmetry, and now you have a preferred direction. So therefore bringing this term, and this term is going to dominate. There could be other physical reasons for introducing this term. For instance, it's known that two components actually see currents of each other, they feel each other. Due to electromagnetic modes, there is a TEM splitting between vortices of two components rotating in opposite direction. Stress, for instance, when the spin is applied, that also creates one particular direction, so that also leads to this term. And the idea that this term now allows the interconversion between the particles. So if I now go back to my use this Hamiltonian to write the Spinor-Gross-Pitaevsky equation with gain and losses again, then that converts into these terms. Similarly, we have the equation, so this is for the left polarization. For the right polarization, it would be the same equation, but the action of the magnetic field, if I go back, the action of the magnetic field will come with the opposite sign. So it's exactly the same, but with negative sign for the right polarization. And so again, we dimensionalize, and we get this system of these complex Gross-Pitaevsky equations. Again, the gain, I will later on replace it with, again, gain will be on a finite radius of the spot. So gain dissipation. This is the action delta represent the detuning due to the magnetic field. This term is going to be negative. So for the UA is about 1.1 as estimated from the experiments. So you have repulsive interaction between atoms of the same polarization, between quasi-particles of the same polarization, but attractive between particles of different polarization. Okay, and so now I'm interested in seeing the interplay between this interconversion term and this detuning. And there are several questions that we can ask. First, we can talk about normal modes of uniform modal. So for instance, again, if we consider the small amplitude perturbations, the small normal modes, then depending on delta and j, these modes can be diffusive, like for the complex Dros-Kutaevsky equation, that can be linear, like ultra-cold gases, or they can be gapped. I'm not going to talk much about this. What I'm interested in these two parts, so I would like to discuss the effect these two terms have on vortices and on synchronization, desynchronization in the system. So these are two questions that I will address. Okay, so the first question is, let's assume that I'm taking two vortices, one of the positive circulation, one of the negative circulation, one vortex in the left polarization, the opposite vortex, the anti-vortex in the other polarization. And then I see the outcome of this configuration. So of course, if there is no interconversion, then two polarizations do not see fluxes, do not see that these vortices have different sign, different direction. So all these complexes, vortex in one, no vortex in another, or vortices of the opposite circulation, are dynamically stable. But so there is no magnetic field, but there is an interconversion. So now two components start feel the direction of the circulation in the other component. So these vortices are still stable because they rotate in the same direction, but these complexes become unstable. What is the outcome of the instability? So for this delta equal naught. So if the inconversion is weak, and remember I start with positive vortex, negative vortex in these two components. So this will be for the left component, this is for the right component. What you see is the density and then the streamlines superimposed on the top of the density profile. The red as before indicates the radius of the pumping spot. So I started with two vortices in the centers, and then if j is small, these vortices are just slightly displaced and they start circulate around the center. If j increases, then both vortices actually left the condensate, leaving behind a stationary wave of depletion, a rarefaction wave, where the fluxes in two components are acting in opposite direction. So there is some preferred axis in this case, and the fluxes are in opposite direction. So the streamlines go in this way for the left component, the streamlines going that way for the right component. If I increase interconversion even further, these vortices that left actually bring about, so one vortex come back, so this is a positive circulation, and the other component has exactly the same shape, so the negative vortex left, bringing the positive vortex in, and the complex stabilized. If I increase it even further, then again, both components have exactly the same outcome of the instability, but in this case, it's stabilized to a pair of two vortices of opposite circulation. Okay. So, but now if I use my detuning, the magnetic field, then I can always, for any j, doesn't matter how big it is, I can always find a significantly large detuning so that this complex is being stabilized. So now you have positive vortex here, negative vortex in there, and this complex is stabilized, although you can also see the wave of rarefaction rotating on the top of this vortex. Okay. I would like to say maybe a few words about this state, because I promised to talk about solitary waves, because this is an example of the solitary wave. This is stationary wave. And we can actually look more closely at it, because we know that the density depletions appear in other systems, equilibrium systems, as dark or black gray solitons. They're also known as rarefaction waves. You heard about this earlier today. We also know, but we are dealing with complex Ginzburg-Landau equation. There are analogs of these traveling waves called Nozaki-Becky solutions. So the question that we were shortly looked at, whether these are indeed relevant. From the simulation, we see that there is a symmetry. So if I call this is y-axis, then the right component is actually completely antisymmetric to the left component. So that suggests that, that my stationary state satisfy this one component equation where I just bring this j. Remember, delta is 0 in that case. So I can go further and I can even look at the solution of one-dimensional equation. Therefore, in this equation, I neglect the fact that there is a radial confinement. And so I can compress, therefore, one of the variables. So that leads to one-dimensional Ginzburg-Landau equation without any trap. And I can look for solitary wave solutions for this system. And indeed, there are solitary waves. There are these holes, rarefaction waves. They exist up to some critical value of j. So the higher j is, the deeper this depletion becomes, the higher the velocity at the center, but then it does not exist for sufficiently large, for j larger than this critical value. So note that without this term, there would be no Nazaki-Becky holes because there is no diffusion that actually stabilize the central frequency of the trap. So the Nazaki-Becky solutions really do not exist if there is no this term in the equation. So we view it as this term actually plays the role of this diffusion in the sense that it's indeed stabilized the central frequency of the pulse, allowing for these solutions. But we don't know anything else about the solution. We don't know we were unable to find their analytic form. But again, we haven't spent that much time on them. But I thought I'll just show you. Maybe someone will get interested in this sort of equations. Okay, what else can we do with the system? I can view it as a two-mode system. So what I'll do, I'll neglect the trapping potential and any spatial variation. So I neglect the Laplacian term. And reparameterize my equation in terms of the sum, half sum and half difference of the densities of two polarizations in terms of the global phase and the relative phase. And of course, the global phase then will not show up in the equation, so we have three coupled differential equations for the relative phase, half difference, and half sum of the densities. We can consider so-called Josephson regime, in which j is much smaller than the half sum of the density, and the half difference also, this is also negligible in comparison with this. In which case, the station, I can neglect that, so my stationary state for R correspond to alpha over sigma. So now I have just two systems for four-dimensional differential equations, and they can be by eliminating Z. We actually have equation for driven damped pendulum. What do we know about driven damped pendulum? That it has two regimes, actually three regimes. It has synchronization regime where the dynamical system has only fixed point. It has desynchronization regime where there is a limit cycle, and then the bistability regime in between. So therefore, that's what we expect from the full system. But of course, we can do it accurately. We can just do it for the these three equations and discover what are the bifurcations. And so now we plot J versus delta, so interconversion versus this detuning magnetic field. And we can see that indeed there is a region of bistability. So if we here, then there are fixed points that correspond to this dynamical system. Here we have limit cycles, and there are various transitions. So this is actually the homoclinic bifurcation for stable cycles that we found quite interesting. And depending how we go, depending on initial state, when we enter this bistability, we may have fixed point or limit cycle. But it's even more interesting for the full system. And actually it turns out that it represents this quite accurately, but it brings something more to it. So now I go back to my fully trapped spinor system with Laplacian back in. And what I'm interested in, first of all, what are the chemical potentials averaged in time? And I can see, so for instance, I will take this corresponds to simple case when there are no vortices, so the vortex, the radius is below the criticality for the creation of the vortex lattice. And we can see that initially, as the magnetic field increases for fixed J, the chemical potentials of both species agree, so they are the same. And then as the system enters this desynchronization regime, then each of the components acquires its own chemical potentials and they become different. This is marginal case when the radius of the pumping spot is slightly below the criticality, so that initial, but since delta causes this criticality, the actual radius for criticality change, effectively change, then as delta increases, there is a sudden drop in the chemical potential that, as we know, implicates the creation of the vortex lattice, but still both components are synchronized, and then there is a desynchronization regime. Actually, this marginal case, if delta is small, we're in synchronization, there is no vortices, no vortex lattice, as for this point, there is a lattice of 4 vortices in each, but it's still synchronized, and now we have limit cycle if delta is large. But actually, even this simple case is not so simple, because when we get, so we're slightly above the criticality, so we are slightly above the synchronization, so we already entered the synchronization regime, then we have limit cycle, and this is, if I amplify this part of the phase diagram, there is this retrograde loop. So it's a doubly periodic solution with respect to the change in relative phase, and this is the retrograde loop. So what is depicted here is theta versus the rate of change of theta, theta being the difference between the phases of the two components. Okay, so this full model, so what are the conclusions about two model in comparison with the predictions of two mode? It has much richer behavior. First of all, there are phase portraits that may have fixed points, limit cycles with different windings. Oops, sorry. We also saw chaotic behavior in this region of bistability. It's quite interesting that we saw counter-rotating lattices in the system. We saw spatially non-uniform interconversion. So, for instance, these two diagrams show the same component, the same polarization, but small time elapsed between these two pictures are taken, and blue shows that's where the mass is being lost at this moment of time. Red shows where the mass is being gained, and that completely changes for the same component small time after this picture. There is also, for another configuration, this interconversion is radially symmetric, but it's non-radially symmetric here. So it's an interesting dynamical system. It agreed with the two-mode analysis quite accurately, at least for small interconversions, but the actual dynamics is much more interesting and worth studying further. So we just picked the top of the flower, really, with that. So let me go to my conclusions, and I would do my conclusions and trying to illustrate some interesting problems that are still open. So what I've done in my talk, I first of all introduced the Gross-Pytaevsky equation with loss and gain as the possible model for non-equilibrium condensate, in particular having in mind exciton-polariton condensates. So I studied radially symmetric, using this model, I studied radially symmetric stationary states and showed that indeed this model predicts the narrowing of the density profile in the middle of the condensate. This model predicted the spiral vortex states, and indeed they've been observed in experiments. Our model predicts also the vortex lattices that they haven't been observed in experiments yet, although we are talking to Pittsburgh group. And again, the problem is that it's very hard to actually increase the radius of the pumping spot. So they're still in this, all the experiments were done in a regime where you wouldn't see the vortex lattice. We introduced the model for non-equilibrium spinor system and analyzed the effect or interplay between magnetic field, so detuning due to the magnetic field, and interconversion. Shortly I told you about the effect these have on vortices. I analyzed desynchronization and synchronization with region of bistability for this system. There is another interesting characteristic of the system that I wanted to mention, that when analyzing the effect of detuning and interconversion of vortices, I always dealt with almost always dealt with either big delta when these plus and minus vortices are stabilized, or small delta, or zero delta. So, but what will happen if I start increasing the delta slowly? So again, go into that case when for delta equals 0, you have just a solitary wave. As delta starts increasing from 0, I still have the solitary wave, it's stationary solitary wave, but now it shifts away from the center of the cloud. As delta increases, there is a rarefaction wave in the left component with a vortex in the right component. As delta increases even further, now I have positive vortex in the left component, negative vortex in the right component, and they are in a precessing motion around the center of the condensate. But the trajectories of them are quite interesting. So they are these spirographs, epitrochoids or hypertrochoids. So you have the black shows the motion of the positive vortex in the left component, and blue shows the motion of the right of this negative vortex in the right component. We do not have a good theory. We have some theory to explain how these trajectories come about by actually phenomenologically trying to combine different effects. So there is a radial fluxes, there is a Magnus force acting on a vortex, there is these terms that come from the interaction of these two vortices, so we can qualitatively see why these trajectories would have to be spirographs, but qualitatively we were unable to actually get these trajectories to any way, in qualitative agreement with what we saw in the simulations. Okay, I think I'll stop here, and if you have any questions.
Yeah, questions, comments?
So in the model equation with the gain and loss, do you have a global mass conservation in the whole domain?
No. Or maybe it's quicker just to write it down. So if I write down the conservation of the mass continuity, even for the steady state, then it will be alpha minus sigma rho rho. So
Right,
it's a
but
steady.
that's a local equation, but if you integrate it over the whole domain, do you have the fluxes at the boundaries, not non-zero fluxes at the boundaries?
So the fluxes are always non-zero, yes. You have to have non-zero fluxes.
At the boundaries.
Not everywhere in the domain. So it's a steady state, but the fluxes are constant. So if, for instance, for this diagram that I present, for the stationary state, which is like that, so that would be the density. Okay. So if I plot the velocity, maybe the amplitude of the velocity, it'll be like that. So it's a steady state, and the velocity is steady. So it doesn't change in time. So there are constant fluxes in the system.
Right, but it vanishes as r goes to infinity.
I mean, it depends on a particular configuration. Like if I have trap, then right, everything has to diminish at the boundary of the trap. I can have other systems, and particularly in the Jacqueline Bloch group. Now, what they do is really just one-dimensional polaritons. So they pump. Let me just. So they pump along the interval. So that's where the pump is. And then the polaritons decay, but at infinity, the velocity actually approaches, I don't know, the square root of alpha over sigma at infinity. So in this case, and it's clear, so if I have gain characterized by alpha, decay characterized by sigma. So it can be seen just from the conservation, because the chemical potential has to be constant, so, and velocity here would be 0, and then therefore it has to have non-zero value away from the condensate. So it all depends on particular physical realization of the system.
Other questions?
I just wanted to go back to the issue of the validity of the model. I mean, clearly the model captures some qualitative features, for example, the shoulder kind of on the profile, but have there been any attempts to try and check its quantitative predictions of experiments, whether quantitatively it can predict features of the experiment?
Quantitatively. Again, in this very recent experiment by Jacqueline Bloch, in 1D, so the actual structure of this condensate, because also, and even depending on the temperature, there was some agreement again obtained from the from this kind of model on what is the structure and what is the height of that peak. This could be circumstantial evidence. I mean, there is no rigorous bound to say, that's what, it has to be. With Jonathan, now we're actually looking at precisely this problem, trying to invent a system using the spinner model, trying to say, change, because now you can change the magnetic field, change the detuning, and that's what you should see, and that's what you can measure, and then you can recover these parameters from your measurements. So we're trying to get this. So perhaps that would be some quantitative justification, or at least put the bounds, because right now we don't even know the bounds for these parameters. That, well, I mean, this is a wide range, going from 0 to 10, for instance, for gain. And also the rate of the dissipation, we can't, again, since we can't get it from the first principles, it's also model dependent. So if we assume that that's the model we have in mind, that's what the estimates and the parameters should be. And that's not the right way to do it, of course. But at the moment, that's the only way, because, again, this is a system for which you cannot get an accurate model from first principles, so you have to do something else.
Okay, then we have now a break, and